let's look at the classical example, right? You can see it anywhere. So let's assume that we have an infinitely long, pretty much from that infinity to that infinity, charged cylinder. So uniform uniformly. So we have a uniform distribution of charges. And let's assume positively charged for simplicity. What is given? Radius of the cylinder is given, right? And rho, it's the volume charge density, right? So you see, now rho is given. Yesterday, when we discussed, when we were finding electric field created by a sphere, the total charge was given. And as a result, we had to find a volume charge density because we needed that. Now volume charge density is given. Actually, in this case, it's even difficult to give a total charge because we have an infinitely long charge cylinder, right? So in this case, rho is given. It means what? It means that at the final result, in the final answer, rho can be present. Right? Don't try to find rho, because very often in the past I saw students, if I give a problem like this, they try to find the value of rho. No, it's given. If it's given in the statement of the problem, it means that it's given. Use it, and it's not bad if it's okay if it is present in your final result. Right? Okay, enough of introduction of the problem, and now we need to find the electric field. Of course, now, again, we have two alternative approaches which can be used to find the electric field. You can use either Coulomb's law, that's what we introduced from the very beginning, or you can use Gauss's law. In this case, yeah, you can use Coulomb's law, but of course, it still will be slightly longer. Integration would take maybe like 15-20 minutes. Using Gauss's law, it's much faster, right? But since we're going to discuss everything thoroughly, of course, we will move a little bit slower than we can move. Okay, so anyway, we're going to use Gauss's law. And again, you remember first step, when you start applying Gauss's law, what do you have to do first? Right? You remember previous class? You have to pick a Gaussian surface, right? So that is the must, because without that, you wouldn't be able to start evaluating this integral, and you wouldn't be able to tell which charge is enclosed, right? And again, you remember you have universal freedom to choose any Gaussian surface you want, right? And since in part A, we want to find the electric field outside of the cylinder, of course, your Gaussian surface must be outside, because basically with a Gaussian surface, we probe electric field, right? So, and again, you can pick any Gaussian surface you want, but of course, you will have consequences, right? If you pick some not the most convenient, not the best surface, you will struggle much more, right? So we need to pick the best possible surface so we can use the symmetry of the problem. And I think the gut feeling should tell you which surface we have to use, right? It should be a cylindrical surface, cylinder, right? But of course, you remember it must be closed. So that cylinder must have, okay, I'm using salt, my box of salt, right? So of course, that cylinder will have this facet, that facet, and of course, cylindrical wall. So because you remember, Gaussian surface must be closed. Okay, so let's first pick the Gaussian surface. I'm going to draw it of a finite length. The cylinder is infinitely long, but your Gaussian surface is going to have a finite length. Okay, so it must be outside, so let me draw it somehow here. Right, so something like this, like that, and like this. And that side is invisible, right? So that's my Gaussian surface of some arbitrary radius r small. Again, r small basically will be our variable. Okay, and that Gaussian surface, of course, is concentric with our charge cylinder, right? Okay, let me draw that it has radius r, right? And let me just label that this is our Gaussian surface. Okay, so the first step done. We picked a Gaussian surface, and this is the best. With this Gaussian surface, we can use the symmetry. We can use the symmetry of the problem as much as we can. All right. So now after that, we can start evaluating the integral. Usually, I start with the integral. But in this case, okay, let me rewrite. Okay, maybe I can write so Gaussian surface. Right. And so let me rewrite this integral to start evaluating it. Okay, first step. What do we have to do first? You remember in the previous class when we have spherical symmetry, we didn't do anything with this integral, right? We just started evaluating it. But in this case, look, we have a significantly complicated surface. We have cylinder, right? Which has different types of surfaces, right? We have these flats, this front side, it's flat, back side also flat, and this surface is cylindrical wall. We have three types of surfaces. In the previous class, when we have a sphere, we had one type of surface only, right? Spherical. And that's why we didn't do anything with that integral in terms of splitting it into several integrals. But now, since we're going to integrate over this complicated surface, we have to split this integral into three integrals, three surface integrals over this facet, and this cylindrical wall in order to integrate it, right? I doubt that you disagree with me, right? So let's split it. But you know what? Before I start splitting this integral, let me label those surfaces, right? So which way I label it? Okay, so the cylindrical wall, I label it as S1. Now where can I label it? Okay, let me label it here. So this is S1. Oh, let me call it wall, cylindrical wall. Then this surface, front facet, let me label it as S2. It's a front facet, front wall, whatever, right? And this back facet, let me label it as S3, back. Okay, so now we labeled all these parts, and now since any integral is an additive thing, so of course we can split it into as many integrals as we want. In our case, we want to have three integrals over each of these surfaces. Okay, so now let me write integral of E dot dA, and you know what? On purpose, I'm trying to estimate the amount of space. Okay, I'll try to fit everything. Then I will, okay, plus. This will be integral over a surface S1, cylindrical wall. This will be E dot dA. It's over surface S2, front facet. And the last one plus integral over S3, back facet, E dot dA. So now I have three integrals. And just for fun, simple question. Okay, from the mathematical point of view, look, here I have this circle in the middle of the integral. How come that I didn't write that circle over here, here, and there? And of course, the answer is very simple. All right, because when you combine all these three surfaces, it's a closed surface, right? It's a completely closed surface. But once you separate this surface by itself, of course, it's a flat surface. It's an open surface by itself, right? This surface, actually, this is cylindrical wall. But anyway, cylindrical wall also by itself, it's an open surface, right? And of course, S3 also by itself is an open surface. That's why there are no circles in these three integrals. But once you put them all together, yeah, they form a closed surface, right? As it should be, as it must be, not should be, for the Gauss's law. Okay, so now now we need to evaluate these three integrals. Again, yesterday we had only one integral. Now we had to evaluate three integrals. But story is not that bad. We just need to look carefully, right? And again, the meaning of these are flux, right? Electric flux, right? Okay, so now in order to evaluate these integrals, okay, we need to, like yesterday, let me draw all these vectors: electric field, area vector, electric field, area vector, and for this integral, right? So let's start, for example, with, I don't know, S3. What is direction of dA? You know what? No, let me start with S1. Direction of dA. Direction of dA, you remember, by convention, the area vector for the closed surface must point towards the outside, right? So if this is our Gaussian surface, of course, dA must be this way, right? Radially out. Of course, perpendicular because it's cylindrical wall, so it's a perpendicular, right, and outward, so it means radially outward, right? Here, here, at any point, right? So I can draw the area vector. Okay, I can take a small patch, for example, on this on the wall S1, on the surface S1, and so this will be my dA, area vector dA. So that's the dA for the first integral. Now, right? Again, if you disagree with something or you don't see that, okay, tell me. But I think so far it should be more or less obvious, right? So now, what about area vector for this surface S2? This surface S2, right? Front facet. Again, you remember, area vector must point towards the outside, must be perpendicular. So this is our front facet, right? I need to cover the brand so that I wouldn't advertise the brand of the salt. Right. So it must must be perpendicular and towards the outside here. So it points that way, right? Perpendicular. So it means that over here I can draw it. Not can, I have to draw it that way. Right. So I can take a small patch, for example, over here, right? And area vector will point this way, dA. So that's for the second integral. And for the third surface, of course, opposite. So if dA on this facet that way, dA for that facet in the opposite direction points that way, right? Okay, so let me draw. Again, I can take a small patch here, and this will be dA for that surface. Okay, great. So now we know directions of all these dAs. So first I need to get all the information about these vectors, and then I will start evaluating, like in yesterday's class. First I drew directions, drew those vectors, E and dA, and only then I started evaluating this integral. Now, what about electric field? Right, electric field. Usually books say something like this: because of the cylindrical symmetry, it's obvious that electric field must be radial. Basically, radial, it means if this is your charged surface, radial this way, right? And then down, and so on, right? I still want to justify it. So let me, again, like in previous class, let me draw a justification on that side, right? Sort of, if you want, but of course, on the exam, I don't demand justification. If you just draw the correct direction of electric field vectors, it's enough, right? But in the class, I feel like justifying. Okay, let me write over here. So justification. Okay. Of direction of E direction. Okay, so let me redraw this picture very quickly. So let's say this is my, okay, our infinitely long charged, okay, I can do better. Right, infinitely long charged cylinder, right? And let's say I want to find direction of the electric field at this point, right? Okay, so let me draw an auxiliary line which goes through, okay, which is perpendicular to the cylinder, right? And now, since we have uniform charge distribution, of course, I can take, for example, some point charge over here, for example, or over there, but anyway, on this side of the cylinder, right, relative to this line. Why not? Of course, since we have uniform charge distribution, at any moment of time, I can take, for example, small piece of charge, which is basically like a point charge over here, plus, right? And of course, this charge is going to create electric field at this point. Basically, it will be its own contribution to the net electric field at this point. So let me draw contribution from this point charge. Okay, let me draw this dash line. So this will be contribution from that red point charge. But again, since we have uniform charge distribution and the charges are everywhere, of course, I can find somewhere over there symmetrically position charge identical to this one, but it will be, okay, symmetrically relative to this line, right? So over here, of course, I can find some, I don't know, blue charge of the same value, right? And which is symmetrical to this one relative to this line, right? So now let me draw contribution from this blue charge to the net electric field at that point. Okay. So of course, it will be something like this. And of course, electric field strength of this and that exactly the same, right? So now, if you add these two vectors, of course, components, horizontal components are going to be canceled, right? And if you add then these radial components, you're going to get, let me complete a parallelogram. So this will be the net electric field. And you see, it's pure radial. And during integration, when you add contributions from all point charges, for any point charge on this side, you can find symmetrically positioned point charge over there, and their horizontal components will be canceled, leaving only radial components. Again, basically, we use symmetry to justify a direction of the electric field, right? So electric field direction is radial. So I can draw, of course, I'm not going to draw over here too much, but I can draw something like this. So the electric field, of course, will be radial everywhere, right? Over here I can draw, right? Or two-dimensional picture. Of course, you can draw three-dimensional, you can try to draw some additional lines, but I don't want. So you see, I think I justified that electric field is going to be radial. Right? Okay, so now, as a result, let me draw some those electric field vectors over here on our picture. On the okay, I will attach them or draw them next to these patches. Okay, first let's start with this patch, right? All right, so electric field is radial, so it will be in the same direction as the direction of dA, right? Radial. In this picture, I'm trying to draw three-dimensional picture, right? So you see, they dA and E are parallel. Okay, now the next, what about this? I want to draw electric field next to this patch. At this point, some students made mistakes because based on the previous class experience, students develop a habit that it looked like all the time electric field is parallel to dA, and they follow that trend, and quite often I see that they draw electric field parallel to dA. No. electric field, we just justified it's radial at any point, so it must be radial, radial, radial at any point. And how come that at this point, yeah, according to those students, right? So just the way you so how come that electric field at this point is in the different direction? It looks like their Gaussian surface, right? Their Gaussian surface, their imaginary mathematical idea, their imaginary Gaussian surface changed the direction of the electric field. Your imagination, your imaginary Gaussian surface cannot change direction of the electric field. If it's radial everywhere, it must be radial everywhere. And that electric field direction doesn't care about our Gaussian surface. Maybe even doesn't know about the existence of our Gaussian surface, right? So even at this point or any other point, electric field must be radial. Guys, be careful, right? At this point, lots of mistakes. So it must be still radial, and if wrong color. All right, and if I try to follow this three-dimensional picture, so this will be direction of E, and of course it's perpendicular to dA. Okay, let me grab my again salt. So what we have, it's a dead surface, right? So area vector this way, electric field, it can be either this way, down, or if area vector over here, electric field is radial, still radial. Basically, not basically, perpendicular to the dA, to the area vector. Okay, be careful at this point because many mistakes at this place. Again, if you don't see that, okay, tell me. I can spend a little bit more time, although it looks like I showed it. So that's direction of dA. I mean direction of E for this integral. And now let's do the same for this. Again, electric field is still radial, perpendicular to this dA. Right. Okay, let me draw over here. Right. So that's E. Right. So perpendicular to dA. So now, since we have all these vectors in front of us, now we can evaluate these integrals. And you know, I'm going to do it underneath, right? So here there will be evaluation of this integral. Over here, I will evaluate the second one, and the first one, of course, will be here. Right? So let me start with the this one. So, all right, let me separate it like this with two lines. Right, these two integrals, evaluation of this integral and that integral. Right, so first I want to show that electric field is perpendicular to dA, sign of perpendicularity. So as a result, what can you say about the dot product of two perpendicular vectors? Okay, anyway, I will write it. So E dot dA, of course, you can write it, no, not you can, you have to write it like E times dA and times cosine of angle between them. You know what, okay, I will write underneath. I feel like I'm not going to fit it. So E dA and cosine of which angle? The angle between those two vectors, 90 degrees. Right, so these are 90 degrees angle, right? So let me show it. 90 degrees. Cosine of 90 degrees. And cosine of 90 degrees, of course, you remember, right? It's 0. Cosine of 90 degrees is 0. So as a result, integrand is 0. As a result, this integral over surface S3 is 0, and we can dump it. Right. Okay, you could have told me this answer from the very beginning once we draw the picture, because you remember just using conceptual justification explanations, look, you remember the meaning of the electric flux, because basically this is the electric flux, the value of the electric flux to this surface S3. And you remember electric flux, it's the number of electric field lines crossing a surface. And in this case, electric field we just show radial, right? And the surface, okay, in this case, basically electric field is vertical, right? Let's say it this way. And this surface, right? So let's say this way. And this surface is also vertical. So electric field vector is parallel to the surface. So basically electric field lines physically cannot cross that surface because they're parallel, right? And again, electric flux, it's a number of electric field lines crossing a surface. In this case, electric field lines just cannot cross the surface, giving us zero electric field. So that's probably the simplest justification of zero value of this integral. So S2 will be exactly the same. And that's the reason why we picked the Gauss, this surface as the Gaussian surface. Because basically, somewhere deep inside, we knew from the very beginning that flux through that surface and flux through that surface will be zero. And we will have to evaluate only flux through the cylindrical wall. So over here, exactly the same. I can write, all right, so here, the same. So I can dump this integral also, zero. And so only this left. And I have plenty of space to evaluate that integral. So I will start probably here from this side. So E dot dA, you know what, no, let me start with different line. So electric field in this case is parallel to dA. For the cylindrical wall, these two vectors are parallel. So E is parallel to dA. As a result, E dot dA equals to E dA times cosine of 0 degrees, and cosine of 0 degrees is 1. So it will be just product of absolute values. Now this integral looks like an integral which we saw yesterday when we discussed spherical symmetry. Right? Okay, so now I will continue this line of integrals underneath. Right. So now let me continue it over here. All right, so here we just evaluated these integrals. Right, so now only S1 left. So it will be integral of E dot dA over a surface S1. Again, you see here we had vectors. Now we have just magnitudes of these two vectors. So we have the same achievement like yesterday after the first step. Right. And now the second step, we need to basically somehow extract or justify extraction of the electric field from this integral. And justification will be very similar. So look, imagine yourself sitting at this patch on the surface S1, on the Gaussian surface. And look, that this distribution of charges give us this electric field strength, because now we have only strength electric field, right? We don't care about the direction of the electric field. It's no longer present in our integral. But if you move yourself from this patch to any other patch on this cylindrical wall, and again, look at the distribution of charges, it will be exactly the same. You will never be able to tell the difference. It means what? It means at this new spot where you sit, electric field strength will be exactly the same. Of course, electric field direction will be different, but strength will be exactly the same. So it means what? It means that it doesn't matter where you are on this surface S1, electric field strength is going to be exactly the same, constant. But again, only on the surface. If you step away from the surface, for example, farther away, electric field becomes weaker. or if you move closer to inside, closer to the charged surface, if you step away from surface S1, from the Gaussian surface, electric field becomes stronger. So this electric field inside in this integral is not uniform, it's just a constant on the Gaussian surface. And again, why can we say that? Because we pick the best possible surface so we can use the symmetry. It's like in the previous class, right? So that's why basically this cylindrical surface is the best. Just now I realized that I forgot to mention, yeah, I told you that this Gaussian surface, this cylinder is of a finite length. I told that, but I forgot to introduce some to show that it had some length. Just now I recall that, so let me show it. So this length is, where can I show it? Okay, I will probably use different color. So this length is L, let's say. It's not given. It's not given. But quite often you can introduce some parameter or maybe some additional constant, right? And most likely, if it's not given in the problem, at the end of the problem, it will disappear. And the same will happen to this L. But at the very beginning, I should have mentioned that that our Gaussian surface, that wall, I mean this cylinder has length L. I just mentioned that it's a finite length, but I forgot to introduce this parameter. Okay, back to this integral. So let me open my next explanation box and I can write, since E equals constant, and I will emphasize on the surface S1. Basically, it's a part of our Gaussian surface. So, and since we integrate, since in this integral we stay on that surface only, we're not allowed to step away, it means that we can extract this this E, right? Since it's constant, we can extract it. Any constant factor can be extracted out of the integral. Okay, so now I can rewrite it. So it will be E and integral. I have a strong habit of desire to draw a circle in the middle. No, but in this case, it would be wrong. All right, so dA, all right, over a surface S1. Okay, so now we're ready to write the value of this integral. Still, again, it's a calculus 3, this integral. But we can, since we know the meaning of this integral, what? Small patch dA on the cylindrical wall is plus area of this small patch, plus area of the next small patch, plus next area, plus, and you keep moving, keep adding these areas until you complete the whole surface, right? And when you finish completing that, when you finish adding all those small areas, what are you going to get? The area of this cylindrical wall S1. Area of this cylindrical wall S1. Area of the cylinder. What can be easier than that, right? Everyone knows how to find area of the cylinder, right? So what do you have to do? You take circumference, right? And multiply by the length or by the height. It depends how your cylinder is oriented, right? So in our case, circumference, and again, you remember we are on the Gaussian surface. So circumference will be 2 pi r small, not r capital. Right now, r capital has nothing to do with the area of our cylindrical wall. So 2 pi r small, see that? And multiply, and I have to multiply by L, length. So L, 2 pi r. So this is equal to 2 pi r times L. Okay, so let me rewrite underneath. So it will be E times 2 pi r times L. So you see, we evaluated a reasonably complicated integral from the point of view of calculus 3. Like that, just because we know the meaning of this integral and we know the answer because you used it in high school, the answer a lot. Okay, so so basically we found the value of the flux through our chosen Gaussian surface. And now back to Gauss's law. So from the other side, it must be equal to Q enclosed divided by epsilon naught. Okay, so that's now what we got from the Gauss's law. So at this point, in order to find expression for the electric field, we need to find Q enclosed. Again, at this point, quite often students just write Q enclosed in terms of electric field, but again, it doesn't lead anywhere. It's just completely useless, right? It's not wrong, but it's useless. So now we need to use basically the definition of Q enclosed, find it, Q enclosed, and then solve it for E. All right, okay, I guess I can put a question mark over here. So now we need to find Q enclosed. And again, it's just based on the definition of Q enclosed. What is Q enclosed? It's the total amount of charge physically embraced by your Gaussian surface. So it means that we need to look at the picture. We need to see which charge we need to calculate, count. So this is our Gaussian surface. So of course, between the this surface of a charged cylinder and our Gaussian surface, this is empty space, and over here it's empty space. There are no charges, right? So charges only over here, right? Okay, let me use blue in order to show which charges we have to find. So I will use something like this. Right, so charges which we need to find are over here. So that's where Q enclosed R is, right? You see that? Again, between our charged cylinder and our Gaussian surface, this is an empty space. Over here also empty space. So charges only over here. Again, you see, physically embrace that only charge. Okay, so now it shouldn't be complicated. Again, you need to recall that slide which we discussed 3 lectures ago, right, about finding charge densities and the amount of charge in some portions of the volume. So the first, it's a 3-dimensional case. So we need to recall that box number 3, right, a 3-dimensional case. And the first formula we don't need because volume charge density is given. So we don't need to find. Again, at this point, quite often, students start struggling. They start inventing the total, introducing the total charge and try to calculate rho. No, 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 no. Volume charge density is already given and it must be in the answer. Or it can be in the answer. Right? So we need to use that second formula from that slide, 3-dimensional case. Right, okay, so I will probably write it here. So Q enclosed equals. So if you remember that formula, what do we have to do? We need to take volume charge density, rho. And what do you have to do with that? If you don't remember, recall the units of rho. You know what? Let me write over here, units of rho. If you have some doubts, what do you have to do with rho? Recall units. Units you remember it's how to find rho. It's you take total charge and divide it by the volume over which it's distributed. So it's coulombs divided by meters to the power of 3. Coulombs divided 2 meters divided by meters to the power of 3. So what do we have to do with rho in order to get coulombs on this side? On this side we have charge, coulombs. So what do we have to do in order to get coulombs? We need to dump meters to the power of 3. So it means that rho must be multiplied by the volume in order to get rid of these meters to the power of 3, in order to get coulombs. So we need to multiply by the volume. Volume of what? Volume of that volume of where the charge volume where this Q enclosed is distributed. All right. So volume of this highlighted region. So let me label it as like V with subscript R, right? Because again, above these points where R equals R capital, this is empty, right? So rho times, so how can we find the volume of this cylinder? Okay, highlighted bluish cylinder. Again, volume of this cylinder, piece of cake should be for you, right? Okay, so you need to know, you need to take area of the base of this wall, right? Okay, of this side area, and multiply it by the length or height, right? Base, area of the base times the height. Okay, so in our case, length is given L, or we introduced, not given, we introduced it in order to go through the solution smoothly. So L is given, and area, it's a pi r capital squared. All right, so now r capital is involved. Over here we had r small because we were on the Gaussian surface. So here you have to be careful with these r's. Again, lots of math on the exam with these r's. But if you understand it, you shouldn't be able to make this mistake, right? So now it's a pi r squared times L. So that's the volume where Q enclosed is distributed. Again, rho stays there, rho is given. Okay, so now you see, reasonably simple. So now we just need to plug back and find the expression for the electric field. So E times 2 pi r times L equals to Q enclosed, this rho times pi r squared times L divided by epsilon naught. I just rewrote this using expression for Q enclosed, which we just found. And you see, so now we can cancel something. First of all, L disappears. We have L on the right hand side and on the left hand side. L disappears as it should be. That's why, of course, L is not given. All right. So we introduced it in order to go through all these calculations nicely. And now it helped us, and now it leaves us. Right. Now, pi can be cancelled, right? And nothing else. Yeah, nothing else. So now we can solve it for E, and now I can write it E as a function of R, right? Because basically this R is our variable. So what's left? Rho times R capital squared divided by 2 times epsilon naught and times 1 over R. Okay, so that's the answer. Let me check if I got to the right point. Yeah. So these, okay, maybe I can put parentheses over here. So these are basically a constant. rho, r, epsilon naught, of course, those are constant. And so electric field decays outside of the infinitely long charge cylinder, decays as 1 over r. Okay, so we can frame it. And I can write it that is for r small larger or equal than r capital. Again, if you don't have to explain everything, justify everything, right? This solution should take you a few minutes, actually, right? But of course, on the exam, of course, I sort of demand justification explanations. Okay, any questions about this part? Here, geometry and picture important. Actually, almost in every problem about Gauss's law, pictures are important. Okay, I can erase this. Still waiting for your questions if you have any. And so now the second part, part B. Let's try to find the electric field inside of this infinitely long charged cylinder. So that was part A. Now part B. So we need to find E inside. Basically, when r small is smaller equal than r capital. So, okay, I need to draw the picture. And yeah, I cannot recycle because it's already tons of information, right? It will be too complicated. So let me draw a different picture over here. And now I kind of zoom in. I will make this our charge cylinder kind of, I will make it look bigger, larger. Okay, so that's our charge cylinder of radius r capital, infinitely long. Yeah, of course it will be charged. Plus, 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 plus. Right. The same is given, r capital and density, volume charge density are given. Right, basically we're just continuing the same problem. And so now, since we want to find electric field inside, and again, we're planning to use Gauss's law. And so first step, we need to pick the best possible Gaussian surface. And of course, that Gaussian surface must be inside because that's where we want to sample our electric field. That's where we want to calculate our electric field. Again, you can pick any Gaussian surface, but you have to be smart and you have to pick the best possible. And at this point, you should tell me basically immediately what will be the best Gaussian surface, right? It will be a cylinder inside of a finite length. Again, we will introduce some L, right? Okay, let me draw. Of course, it must be concentric. So centers the same. They share the same center. All right, so let me, you know what, I'm not going to use dash line. I will use solid line, but of course you understand it is inside. Too much of solid lines, difficult to draw, right? You know what, no, I don't like it. The way I draw it. Ah, slightly better. Okay, over finite length L, right? But again, L is not given. We just introduce it in order to get through the calculations. Right? And of course, of some arbitrary radius r small. And uh, probably I will write the integral E dot dA And so pretty much at this point, you need to repeat all these steps. And all these steps up to this point are going to be exactly the same over here. Not a single symbol is going to be different. All of this up to this point will be exactly the same. Again, all these DAs and E exactly the same. Okay, I will draw those vectors right very quickly, and then I will just write exactly the same way. We can get to the same point, like yesterday's problem, right? As I said, in exactly the same steps. Even the picture is the same. Just the whole picture, all this Gaussian surface was shrank and positioned inside. Otherwise, it's exactly the same, right? Okay, and as a result, so I just jumped to this point, right? So that's what I wrote. E times 2 pi RL and equals to Q enclosed over epsilon naught. So now we need to find, again, as here, Q enclosed. Right, so Q enclosed. And again, let's show on the picture where that Q enclosed is, right? Again, it's the all charge physically embraced by the Gaussian surface, our Gaussian surface we see. So the charge which we need to find is within this our Gaussian surface, within this cylinder. So that's where Q enclosed is. Again, it's just a cylinder. How can we find the charge inside? Again, it's a three-dimensional case. You need to take volume charge density. And again, if you don't remember what to do, look at the units. Rho has units coulombs divided by meters to the power of 3. So again, you need to multiply by the volume over which your charge is distributed. In our case, our Q enclosed is distributed in our Gaussian surface. So we just need to write down the volume of a Gaussian surface. Again, volume of a cylinder. At this point, you shouldn't have any troubles with the volume of the cylinder, finding the volume of the cylinder. Again, area of the facet times the length. Area of the facet, now it's a pi r small squared. So it will be, let me write, so V, volume of the cylinder with radius r. Right? Okay, so let me write it down. So it will be rho times pi r small squared times L. So you see it's different. Over here we had R capital, because over there our Q enclosed was pretty much all the way to the end of our charge cylinder. But now, no, this, we have a charge over here, but we're not counting the charge. So now it's a pi r small squared times L. Right. Okay, so that's the charge, Q enclosed. Now we just need to plug it back to the formula and we're done. So now it will be E times 2 pi, I'm just rewriting this, R times L equals to Q enclosed pi r small squared times L divided by epsilon naught. So I just rewrote this with the expression for Q enclosed. And so let's cancel a few things. Again, L goes as it should be, length of our Gaussian cylinder. Then 1r can be cancelled, right? And pi goes, right? So as a result, we can write down the final answer, electric field as a function of r. R is smaller than r capital, equals to rho divided by 2 epsilon naught. Rho divided by 2 epsilon naught. And r is in the numerator. Again, I will put this bracket, parenthesis, to emphasize that this is basically a constant, and electric field increases linearly if you are inside of this cylinder. Okay, so let me frame it and remind that this is inside, so R small smaller or equal than R capital, right? So part B. So outside it decays as 1 over R electric field. Inside it grows as as proportional to R. Okay, let me plot like yesterday. You remember I plot electric field versus R. The only thing I noticed on the y-axis I drew E as a vector. No, that vector shouldn't be there. It was just an electric field, a magnitude of the electric field. I was just when I watched the video I realized, damn it, that vector shouldn't be there. But again, it's not a crime. So now let me plot electric field. Over here I put the vector sign, it shouldn't be there. All right, versus R, and let's say this is the surface of the cylinder, charged cylinder, R capital. So inside it grows linearly. So it's something like this, dash line. And outside decays as 1 over R. So here it's proportional to R, here it's proportional to 1 over R. So that's how electric field changes with R. Okay, so now in your homework, this is your homework problem, but in the book, the problem is given in terms of linear charge density. Not rho, but lambda. Okay, let me show you how to make a transition using part A, for example. Okay, so let me probably separate it like this, right? And let me write something like this. What should I write? Okay, you know, it's for your homework, right? Right, for your homework. Right. Okay, so you know what? First, I want to start with units of rho and units of lambda, and then we will connect them. And I feel like erasing that picture. Okay, maybe I will have enough space. Right. So let me write first linear charge density. Wait, linear. All right. Charge density lambda. All right. And units of lambda is, again, you remember what is lambda? It's the amount of charge per unit length. So take charge and divided it by the length. So it means units, coulombs divided by meters. Again, you can look at that slide which we discussed like 3 lectures ago. So it will be units, coulombs divided by meter. You know what? No, I need to erase this. Then volume charge density. Volume charge density. All right, so rho and units, we already mentioned it today. In order to find that, you need to take the total charge and divide it by the volume over which that charge is distributed. So it will be coulombs divided by meters to the power of 3. Okay, so now remembering this, let's write Q enclosed, this. In part A, first using rho. Okay, actually we already wrote using rho. And also we can write that using lambda. And once we write it, the same Q enclosed using rho and using lambda, that will allow us to see the expression which relates these two densities. And then using these results, you can rewrite in terms of lambda. Right. Okay, let me do that. I will write, all right, so part A, using part A. All right. Basically this part. Okay, so I just want to write this Q enclosed. Q enclosed. Of course, using rho we already wrote, so I will just rewrite it. So it will be rho times pi r squared times L. Okay, so that's how we can write it in terms of rho. Now, how can we write it in terms of lambda, linear charge density? Look, again, if you hesitate, if you're not confident, what do you have to do? Look at the units. What are the units on the left-hand side? Here we have charge. Coulombs. On the left-hand side, we have coulombs. So in order to get coulombs out of this lambda, what do we have to do? We need to take your lambda and multiply it by the length over which this charge Q enclosed is distributed. So you see, here we multiplied it by the volume because you see inside we have meters to the power of 3. So rho must be multiplied by the volume over the charge is distributed. Now it's even easier. You take lambda and multiply by the length over which that charge is distributed. Okay, Q enclosed. So I will write over here lambda times which length in part A, so our charge Q enclosed is distributed over this length L capital. Right? So we need to take lambda and multiply it by the length over which the charge is distributed. Here we multiply it by the volume over which charge is distributed in order to get Q enclosed using rho, but with lambda it's even easier. It's easier. Okay, so now lambda times L. Right. Okay, so now using this part, we can relate these two densities. How to, which expression to use in order to rewrite these formulas in terms of lambda. Or if you don't want to use these formulas, right, for your homework problem, just Q enclosed lambda times L. Over here you will have Q enclosed equals to lambda times L, and then you can complete the problem. It will be even simpler, right? But for part B, I suggest you to use this transition. Okay, so now let me write. So rho equals L will be cancelled, so rho will be equal lambda divided by pi r squared. So lambda divided by pi r squared. So that's the transition. That's how you can move from rho to lambda. You can just grab this result and plug it, and you will get the relation, and you will get Q enclosed in part B in terms of lambda. Okay, so let me frame this. So that's what you need.